Hi there, and welcome back to our discussion of hash join in the context of chapter 12 in the DB2 course. Of course, it's expected that a hash-based join algorithm has some main memory requirements if we want to build the hash table that holds all the rows of the build table. But working memory may be tight, or the input tables, maybe the build as well as the probe table, can be very large. Well, if working memory is tight, there is a variant of hash join that can be applied anyway, and it's the so-called hybrid hash join because it has some potential for parallel evaluation. It's sometimes also called the parallel hybrid hash join. This variant of hash join proceeds in many iterations, in many rounds. So building a single hash table and probing against that single hash table will not suffice anymore. We have to partition the input, the problem size in a sense, and then iterate over the partitioned hash table that has been created and perform multiple probing rounds. Let's quickly sketch what's going on here. So the situation is, the initial situation is the same as before. We of course got a build input and we've got a probe input, and this is the same setup as we've seen before. In the build phase, we can expect the working memory, this is the working memory, to only have sufficient capacity to store a fraction of the entire hash table that has to be built. All right, because we know that we prepare ourselves to store many batches, many fractions, many partitions of that hash table, not in main memory, but on disk instead. Okay, right. What rows belong into the batch 0, the first batch that can actually be created in main memory, and what rows actually belong into the other batches, the other hash table partitions that will have to be placed on disk, is decided based on the hash value. All right. So we would simply read the rows of the one table, of the build table here. All right. Each of these rows would have a particular A value. The A value would be input to the hash function. We would look at the first few bits. Well, in this particular picture, it would be the first 2 bits. I'm sorry. The first 2 bits of the hash function result. The first 2 bits will decide where the row has to go. If the first 2 bits indicate 0, 0, this would be an indication for the batch 0, and that particular row would be placed inside batch 0 in working memory. Or other combinations of bits here would either lead to a batch 1, 2, or 0 placement, and that particular row would be routed onto the batch partition, the hash table partition that has been placed on disk. All right, so looking at the first n bits of our hash function result would result in the creation of 2 to the power of n batches. We will see that if we have a look at the PostgreSQL plans, you will indeed see that the number of batches created is always a power of 2. So PostgreSQL indeed applies this strategy to partition the hashed rows into batches based on the first leading bits of their hash value. All right, so that would be the build phase. The output of the build phase would be 2 to the power of n partitioned hash table fragments, one of which would be placed in working memory. On the probe side of things, we would act just the same. We would read all the many rows here, and we of course would apply the same hash function to the join column, which is the A column in our playground examples. Some of these hash values will have 2 leading 0 bits. They would immediately be compared to the associated buckets of rows that we have constructed in main memory, and that would immediately lead to the result creation of the first join partners here. All other rows whose hash value starts with 10, 01, or 11 would be placed in the in the others these 2 to the power of n minus 1 batches on disk. All right. So only for the rows that have 2 leading 0 bits, everything will remain the same. All other rows will be placed in their associated batches on disk for later probing. Okay, that would conclude the 0th round of building and probing. Okay, on the next round, we would evict this hash table fragment from working memory and instead load the batch 1, this prepared other partition of the hash table, into main memory. And probing would of course then be performed using the rows in the first batch on the probe side. Okay, we know that the rows on the build side here in batch 1 and on the probe side in batch 1 agree on the first 2 leading bits. So indeed these should be associated and these should be probed against each other. Alright, so that would be the second batch, and of course we would continue like this and load the build side of things into working memory and then probe with the associated probe batch partition from the right hand side of the picture here. Alright, now it should be immediately clear where the potential for parallelism derives from. Once we have created these badges and they are ready for consumption, we could of course have 2 to the power of n processors performing the building, or rather the probing against the individual build partitions here on the left hand side in parallel. So indeed all the probing could be performed in parallel. No cross matches between batches on the build side and the probe side would be possible. All of these batches could be evaluated in parallel. All right. So there's some potential for some performance gain here that results from our initial effort to partition the inputs into these 2 to the power of n batches. All right. A few more details here. So, well, if the working memory indeed cannot hold the entire table, then as I told you, we split the build input into 2 to the power of n batches. We've already talked about this. All right. So the probe input would be in batch 0 would be considered as normal. All right. Or other rows would be processed in the later 2 to the power of n minus rounds, potentially in parallel. All right, so this just repeats what we've just already said. There is an interesting tweak to this idea. There is a modification to this idea that takes care of the fact, or that considers the fact, that the distribution of values in the inputs in the input tables might not be uniform. There might be particular join values, A values in the join columns, that are more frequent than others. And this is an observation that is typically referred to as skew. There is a non-uniform distribution of values in the join columns. Some A values are super frequent and will thus have a much higher chance of finding join partners over in the probe input. All right, so some implementations of hybrid hash join react to that and save some spot in the working memory for a so-called skew batch, even if the hash function for a particular row would indicate that the row has to be placed on some on-disk batch. If that A value is super common, if it belongs to the most frequent A values, and indeed the PostgreSQL database system, any database system, has a protocol, has internal tables that keep track of the value distribution, of the common value distribution in the tables. Actually, this is what is being updated and built when we perform an analyze on a table. So the most frequent, the most common values in each column, they would be identified and then recorded and used to decide whether a row that would maybe placed on an on-disk batch file should rather go into the in-memory skew batch, because it has a high chance to find join partners in the probe input. Okay, if this is not the case, then we will just place the row in its associated batch as is common. All right, so that would be one tweak to the idea that helps to speed up join operation here. And if we switch over to the terminal, what we will do in a few seconds, you will see that indeed this skew idea is also implemented inside PostgreSQL. Let's first check how PostgreSQL reacts if we gradually reduce the amount of working memory, and how this leads to more and more rounds being performed on smaller and smaller hash table partitions. Okay, so this is the terminal again. Of course, we are operating on our one and many tables. We have seen these many times before. I don't think I have to show them again. What we should check is how the working memory is currently configured, because available working memory is the crucial configuration factor when it comes to the relation of hash join. Currently, we are operating with the default of 4 megabytes. All right. So let's evaluate this equi join between one and many on the A columns, as we have done before. All right, hash join has done its job. Let's first check that we are already actually talking about hash join here. Yes, looks good to me. This is indeed a hash join. On the hash condition that we are expecting, the probe input is the larger table, the many table. Okay. The build input below the hash node, the hash construction abstraction here that is placed inside the plan, is performed over the smaller one table. All right, the hash table that we are building has 16,384 buckets, and that fits the memory of 714 kilobyte, which is way less than 4 megabytes of working memory that is available. Given that this is a largely idle database system, there are no concurrent users on this laptop currently, at least I hope so. Well, all of the 4 megabytes are dedicated to the processing of my queries, and as such 714 kilobytes easily fits into the 4 megabytes. No need for multiple batches, and looks good to me. All right. What we also don't see is, well, a particular indication of temp written and temp read that would be added to these buffers annotations here. As soon as we see these, that's an indication that temporary batches, hash table partitions, have been written to disk or read from disk. But currently there's nothing to be seen like that. Everything could be performed in main memory. This might change if we decrease the available working memory. So this is only 1/8 of the earlier available working memory. It's only 512 kilobytes. That's already some constraint. Let's perform the same query again. Now we could start to see batching. All right, so this already took a bit longer. This is still a hash join based plan. All right, that looks okay to me. The decision to place many in the probe and to place one on the build side has not changed. But well, now the available memory space only admits the creation of hash buckets that have 8,192 entries. All right, so the system decided it's time to split the hash table into 2 parts, into a batch 0 and into a batch 1. So all in all, we've got 2 batches. One of these batches occupies 368 kilobyte, which is below the working memory size that we have set ourselves. So we can operate in memory, but at the cost of having 2 rounds here. Okay, indeed, there is some temp I/O behavior to be seen. We have to write, when we construct the hash table, we indeed have to write to temp files on disk, and this actually reflects the creation of the batch number 1 that has been created on disk. And of course, later on during joining, we have to then read that batch again. Okay, so there's also some write activity here, which I cannot actually contribute or attribute here, but well, there's temporary read and write IO activity here. That of course contributes to the slowdown of the entire endeavor. Okay, let's be even more scarce regarding working memory and reduce to 256 kilobytes here. All right, so all this batching should be more serious now. All right, so hash join again. We are looking at the build input currently. Now, well, the number of buckets has reduced once more. It's halved now. The number of batches has been doubled. Indeed, the batches which have been 1, then 2, now 4. The number of batches indeed appears to grow in powers of 2. And at home you can just experiment with further reducing working memory and then see that we will end up writing 8 or 16 batches. Okay. Well, there's indeed the write activity that we see to create these batches on disk. Right, and there is considerably IO activity during the hashing phase that will then access the build and probe batches that have been stored on disk. All right, so all of this is to be expected. This is just the price we have to pay for this hash join based approach. Okay, now for the skewing. Right, so the value distribution in the one and many tables that we have created as playgrounds, well, that would be considered rather uniform, right? So each of the rows on the one side has an average number of 50 join partners on the many side, and that's almost completely uniform, right? So that would be, well, of course, this reflects that this is an artificial playground workload that we have constructed to guide us through all of these experiments, but maybe now it would be time to create some really skewed workload here. And this is what I'm trying to do with this many one table. This is a table that is like the many table, but as you can see, well, all of the rows, all of the 500,000 rows, they carry an A value of 1. This is super skewed. Of course, this is just to amplify the effect of skewing here in this experiment. Again, this would be considered rather unusual or maybe completely hypothetical, but for this experiment and for the demonstration, this would be just right. Okay, so it's super skewed. All of the A values are 1. There's exactly one row over in the many, over on the one side of things that will find join partners, but it will find plenty of join partners here. Okay, so I've already created this table just to save us some waiting time. I've already analyzed this table, which is super crucial now because this unusual distribution of A values, that should be known to the system so that it can properly react and, well, maybe employ skew batching in its multi-round hybrid hash join evaluation. So let's look whether the system indeed took record. Well, let's analyze the table again. Okay, so and now let's look at the internal statistics that the PostgreSQL has saved in its own catalog files, catalog tables. We will look at the statistics for the many one table, and we are particularly interested in the distribution of values in the A column, of course, but for good measure, we will also look at the distribution of values in the C column here. All right. Well, this PG stats table has all sorts of interesting statistical information about the distribution of values inside your tables. I can only invite you to have a look at the PG stats table, look at the documentation of PostgreSQL on that particular table. It's a treasure trove of interesting stuff, and it's really eye-opening on what level of detail PostgreSQL tries to analyze the underlying data in our tables. Okay, so let's look at the stats here for the many one table. Okay, so the output is rather longish. I apologize for that. But what we see here is actually two rows of output. Two rows of output. One row for the A column. Okay. And for that A column, we have an output that tells us how many distinct values are to be found in the A column. And well, there's only one distinct value in the A column. And well, of course, it's the one value. We see actually that particular frequent one value. We see that saved here in this array. So the most common values, this is the column label that is associated with this array. The most common values, they are recorded here in inside the stats table. And of course, these would be just the values that indicate that the placement in the skew batch could pay off. The most common values should be placed in the skew batch. All right, well, we can also see that there is a fraction of null % of null values in this particular column in the A column. All right, in the C column, well, the picture is a little different. This is the C column. There is quite a distribution of values in the C column. Well, given that there is 500,000 rows in the entire table, in the many one table, there's only 101 C values that we will find here. 101 different C values, which is of course the number of join partners that or the number of the join partner that we have recorded here in the many table. Well, there's all of these values from 0 to 100. They are found in this C column. That makes for 101 distinct values that are found there. And here you can see a distribution of values. Indeed, 0 is the most common value, followed by 7, 4, 10, and so on. This is the distribution of common values, of the most common values inside the C column. Based on this information, PostgreSQL during batching, during skew batching, will decide that some rows may be placed in the skew batch instead of finding their way on some on-disk batch storage. All right, so well, if we now repeat our query 11, our join query from above, but of course use the many one table now as the right-hand side table, then let's see how the system behaves and how hash join behaves now. Okay, so still a hash join has been performed, and still the many table is the probe input, and still the one table is the build input. Okay, the number of batches and the size of buckets has not changed here. So given the same working memory requirements or restrictions rather, well, we see the same setup. So hybrid hash join has prepared to create the same number of batches as it did in the query case above. But there is an important difference. There is an important difference. If you look at this upper part here, where we were recording the I/O activity that is performed during the true probing process, then you will see that the I/O activity is super little. Well, if you compare this to the non-skewed plan, let's look. We saw thousands of reads and writes on the temporary files, on the temporary batches that have been created. We don't see that in the skewed case, where almost all, well, actually all the rows of the many side, all on the many rise side, all the rows on the many side could find their way into the skew batch. They didn't actually end up in the on-disk batches and could be processed in main memory, just as we would hope for. All right, so much less I/O activity in the remaining rounds, if any at all, actually. So indeed, skewing in this particular case has been exploited by the implementation of hash join. Placing rows in the skew batch saves them from going to disk, of course helping the performance of the entire join operation here. All right, so that would be hash join under, well, severe memory restrictions, but with the exploitation of skew if it's present in the underlying tables. Well, I think that should conclude our discussion of hash join in the course of this DB2 in summer semester 2020. There's more to be said. There's entire stacks of papers to be read on variants of hash join. If you found interest in that, I am glad to hear, and I can only encourage you to dig deeper there. There's so much more to explore in join algorithms for relational database systems. But let's call it a day for the discussion of PostgreSQL-based joining in chapter 12 here. We will have, I think, 2 videos coming up on the join operation and the join processing in MonetDB, which is of its own interest. And that would then finalize our chapter 12. And I thank you for your interest in performing joins with PostgreSQL, and look forward to see you in the upcoming video, and then maybe for chapter 13 and 14. Take care. Bye.